Good afternoon, everyone. So we were making our way through the implementation strategy in PyTorch. We said it was 5 steps. So the first step is we construct some objects that hold the data, and then we construct the network, then the optimizer and the loss. Finally, we fit the parameters, train it, and then we apply that network. So we made our way through the first few steps, got to fitting the network. We saw that the loss was decreasing over the epochs and the accuracy was increasing. And then we got to the point where we wanted to construct some of the other plots in the demo. So one of the plots we want to construct is this one, which shows, plotting the dots is easy. We want to plot that reddish shape in the background. That's the activation or the network output as a function of x0 and x1. So what we do is we construct a really dense grid of many points, many x values. And in particular, we're going to take 100 points in both directions. So we're making a 100 by 100 grid. So what we do to start is we first make 100 points for x0. Those are going to be from 0 to 1. And then we make 100 points for x1. So that's just with NumPy linspace. But the next part, I don't know if you've seen this. You can also do this in MATLAB. It's called mesh grid. And so what you do is you construct 2 matrices. They're going to be x0 mat, x1 mat. And what x0 mat looks like is it's a matrix of size 100 by 100, where the x1, the number used for x1 at all those locations is constant, but the number used for x0 increases according to the x0 grid. And then we have a similar matrix for x1, where it's a grid of 100 by 100 points, where as you go in the x0 direction, it's constant, but as you go in the x1 direction, the values are taken from our one-dimensional x1 grid. And so now we have these 2 different matrices, and we're going to unravel each of them. So we're going to convert them into long vectors, and we're going to stack them next to each other. So the first value of every pair will be taken from x0 mat, and the second from every pair will be x1 mat. And once we stack them like this, we are going to get a list of pairs that will go through x0, x1 pairs that will go through every point on our grid and give us the corresponding x0, x1 values. So now we have this long list of 10,000 x0, x1 pairs, and that's what is in xplot. And we want to evaluate every one of those 10,000 points by putting it through our network. So that's the plan. So to put it through our network, we first have to convert it to a torch tensor. Then you can see we just do model xplot tensor, puts it through the network. Then we have to get it back to NumPy, so we detach it to NumPy. And this is going to be a vector of the activation at each one of the points on the grid. So that's going to be a long vector of 10,000 points. And so we want to convert that to a matrix like this, so we can plot it. So we just reshape it to 100 by 100. And then we can plot that. We can do this. So we want, instead of x1 going from 0 to 1, we want it to go the other way. So we do this flip UD, and then we just use imshow to plot it. We plot this color bar, and that's how we create this reddish shape. So basically, we're just creating a list of all the x1, x2 pairs in that big grid, putting them all through the network, reshaping the output back into a matrix and plotting it. Okay. Is that clear? Okay. All right. Now we also have this plot where we want to, again, as a function of x0 and x1, we want to plot the hidden activations using these heat maps again. And we also want to plot, for the output layer, we want to plot the weights, the 4 weights of the output layer. So we have to extract those values. Okay, so how do we get these plots? So we're going to take our xplot tensor, which is what we made before. And now rather than putting it through the full model, which has 2 layers, we just want to temporarily make a new model that's just the first layer. We can do that by extracting the dense 1 part of our model, putting our data through dense 1, and then putting that result through model activation. And so that will be the hidden outputs. So those are torch tensors, so we have to detach them to NumPy. And finally, we get something we can plot. And as you can see, it's just we need to reshape that again into a 100 by 100 matrix. And yeah, eventually, I think down here, we flip it and we plot it with ImShow. And so that's how we create each one of these plots. And then the way that you get the weights out of one of these PyTorch models is you do model state dictionary like that. That exports the state dictionary, which basically contains all the weights, so all the parameters of the network. So you can access state dictionary dense2.weight and dense2.bias, and we're just going to call them WO and BO, and then that's what we plot these WOs in the titles of the plot. Okay, so that state dictionary is how you extract coefficients.
Why was dense 2 weight up there? We ran it through dense 1.
So yeah, we ran it through dense 1 to get these pictures, and then in the subplot titles, we're plotting the output weights. So we're trying to get these numbers out of the network. Yeah. Because together they explain what happens in the end. Yeah, so that's why we got dense 2 weight. We didn't really need to get dense 2 bias out, but they come together. So we're just showing how you can get both of them. Okay, so any questions so far? All right, so we're almost done. So we're going to now take a very similar network and apply it to MNIST. MNIST is what we saw last unit when we did support vector machines. The only difference between this network and the one on the previous page is we're going to use a cross entropy loss because we have 10 classes. So rather than using, the last network was for binary classification. Now we just have 10 outputs, cross entropy loss. I don't think I would have to look at the code. There's a second demo. Probably there was no output activation function at all. You don't really need one. So this cross entropy loss is used for training. And then we're going to use 100 hidden nodes instead of 4 because we need more hidden nodes for this more complex problem. And we're going to use 50,000 training samples, 10,000 test samples. And this is what happens as you train it over the epochs. You can see that the training accuracy increases and it's getting closer and closer to 100. Meanwhile, the test accuracy is more or less saturating at a little bit higher than 97%. And that's actually pretty good if you remember with the support vector machine. The support vector machine at the radial basis function, I think got 97.1. So this really simple neural network with 2 layers is basically doing about the same. We didn't use this many training samples for the support vector machine, so maybe in that sense it's not quite fair, but they're roughly equal in terms of performance. But one thing to note is that with the neural network, it takes a while to train it, but once it's trained, it's very fast. Because once it's trained, all you have to do is push the data through it, which basically involves 2 matrix multiplies and a few simple nonlinearities. So putting the data through it is extremely fast, whereas for a support vector machine, even after you fit the model, it's slow to apply it. Because if you remember, the way it works is you have to compare every test sample to every support vector. And if you have a lot of support vectors, it takes a lot of work just to even classify a single test sample. So this is what I mean, a neural network is much faster to apply. Okay, so that's MNIST. Now, so in general, when you design these neural networks, at least 2-layer neural networks, there's a number of things that you want to choose for the performance to work, to get good performance. So one important thing is how many hidden units do you use? If you don't use enough hidden units, the performance is definitely not going to be good. If you use too many hidden units, there's a possibility of overfitting. So generally speaking, you usually just try a number of different values to see the trends. Another choice is the type of hidden layer activation functions, sigmoid or tanh or relu, whatever you want. And then in terms of the optimizer, there's a number of details. First, you have to select the algorithm, like do you use Atom or something else. The learning rate's also important, as we saw. And with these neural networks, it's also popular not to use a fixed learning rate, but actually change it over the iterations. So one popular strategy is you start with a high learning rate, and then you decrease it over the iterations. But there's also many other strategies, and we will discuss this more in the next unit. So that would be called learning rate scheduling. Another thing that matters is the batch size. The batch size and the learning rate together, they have to be chosen. Remember, because as the batch size gets smaller, you have to reduce the learning rate. Generally speaking, as the batch size gets bigger, it's more efficient with computational hardware, especially with the GPU. So often when you're using a GPU, you just get the maximum batch size that you can before you run out of memory on your GPU. And that trains faster. Of course, you have to adjust the learning rate proportionally. And finally, you have to decide how many epochs you want to run for. And there's other things you can do. You can use L2 regularization on the weights. The way that you do that in PyTorch is you actually do that through the optimizer. So when you specify the optimizer, you can specify weight decay, and that corresponds to L2 regularization of the coefficients. And that can sometimes help a little bit. So as you can see, when you design a neural network, there are a lot of different things you can do to try to influence its performance, and a lot of them do matter quite a bit. And so, one approach is to play with things by hand, try to get a sense of how these different things are affecting your performance. Another thing you can do is if you have a lot of compute power or a lot of patience, you can use what they call a hyperparameter optimization package. A popular one right now is called Aptuna. All these things here, these are all called hyperparameters. So this package, you can tell it you want to search over a certain set of different hidden units, certain set of activation functions, optimizers, learning rates. You can tell it these are all the things you want to try. And then you can either do a grid search where it tries every single combination, which can take a long time because of how many combinations you get. Or it has smarter search functions where it sort of randomly tries things, and depending on how well those work, if it works well, then in subsequent iterations, it puts more emphasis in that region of your tuning space. So it tries to make smart decisions based on what it has learned from previous combinations of these hyperparameters. It tries to make a smart decision about future ones to try. And so for the final project, this is something that you'll need to do, and you're welcome to use either of them. From what I've seen in previous final projects, they work about equal. So people that spend a lot of time, or let's say they're thorough in terms of optimizing all this stuff, usually when they try Optuna, it doesn't work that much better or any better. It's very similar. And it can take Optuna a long time to run depending on your hardware, depending on how many things you ask it to do. So it's really up to you. But if you really just want to try a whole bunch of stuff and let Optuna do it and sit back and wait a week or so, that's certainly an option. Yeah, I mean, it really just depends how many different options you give. But right, if you give 5 of these and 3 of these, that's 15, and then if you give it a couple of these, that's 30, and then if you give it like 3 of these, that's 90. And it just grows and grows and grows the number of networks it has to train. And generally speaking, when you do all this, you don't use cross-validation because it's like k-fold, because that would be too expensive. So you just have you take your total data, you split it into a training set and a test set, and you just train on the training set and evaluate on the test set. It would be better if you had the compute power to do k-fold, but it just means training, many more models. And usually it takes long enough to do this once that people don't want to do this k times. Okay. All right. Any questions on this stuff? Okay.
Isn't there a way to specify a device on here? I'm just asking how to specify a device to train on.
Oh, like if you have a GPU?
Yeah. Some of the newer Macs. Also, but yeah.
Yeah. You can find all that stuff in the PyTorch documentation. So it's relatively easy as long as your hardware is compatible with PyTorch. So I don't know if the newest Mac stuff is. I don't. I've seen a few web pages that suggest that the newest Mac processors are, but it is a bunch of work to get it all actually working, and I haven't tried it myself, so I don't know.
Okay.
But if you have like GPUs that are like NVIDIA GPUs that support machine learning type stuff, and let's say you have a Linux machine or Windows machine, it should not be too difficult to get it working. You have to have the right CUDA and all that stuff matching your hardware. Okay, so one other thing, actually the very last thing to talk about is that when you work with classification and you want to do something like binary cross entropy, there's 2 ways to do it in PyTorch. And we talked about this a little bit before, but I just want to reinforce it again. So one way to write the binary cross entropy loss is in terms of these z's, which we call scores. They're also called logits. That's the way that we derived it back in Unit 5. There is another option. You put the logits through your sigmoid activation, you get these A's. These A's are the ones between 0 and 1. And now you can also write the binary cross entropy loss in terms of the A's. And either way is fine, but you have to make sure that you use the right function in PyTorch. So if you want to use this model, where the last thing in your network is a Z, and that's how you specify your loss, then you have to use BCE with logits loss. On the other hand, if you have a sigmoid layer in your network and you output the A's and you define your loss with the A's, then you have to use BCE loss. If you get them mixed up, your performance will be terrible because the loss is completely wrong. So just remember that you have two choices here, but whichever you choose, you have to make sure to choose the right loss. And the same thing happens in the case with more than two classes. If you want to use the logits, then you use cross entropy loss. If you want to put them through a softmax and get these activations, then you use NLL loss. So this blog post talks a little bit more about this, but I've seen students make this mistake often, so that's why I'm emphasizing it. All right, so that's all I have to say for this unit. Are there any questions on anything here? Okay, so then we'll move on to Unit 9. So in this unit, we'll sort of start with our knowledge of these two-layer networks and then talk about recent advances and extensions to convolutional and deep networks. And just to start at the beginning, we actually have to talk a little bit about data. So a lot of what the way that I'm presenting these set of lecture slides is kind of historical. So we're going to start at the beginning of deep networks and understand what was done, understand what the problems were, how people solved those problems, how you got the next generation, what the problems were, how those were solved, and so on. So we'll see an evolution of different types of deep networks to understand, what matters, why it matters, and all that. So just to begin that whole story, we have to talk about data. And so the thing to know is that before 2009, when people worked on image recognition or image classification, they worked with small data sets relative to what we have today. So for example, we saw the MNIST data set in the last unit. So that has 70,000 examples, 10 classes, with 28 by 28 images. So these are really pretty tiny images, if you think about it. Other similar data sets that were popular around that time were Pascal VOC, Cipher 10. Cipher 10, these things are still used quite a bit just to play with things because they're small, simple, easy to train, all that. So people still use them. But let's say Cipher 10, which is the one we're showing here, that has 60,000 examples of 10 different classes, and these are 32 by 32 color images. So similar size to MNIST, but instead of digits, the classes are these: airplane, automobile, bird, cat, and so on. And here are just some examples. As you can see, the images have just enough resolution, barely, to figure out what is there. Like, if you didn't tell me that this was an airplane, not sure that I would know, but okay, maybe it is, and so on. But this is, essentially what you're working with Cipher 10. There's also Cipher 100 that has similar size images, 100 classes, and so on. But this is what people used. This is the only options that they really had to work with prior to 2009. And even at that time, these things would stress the compute hardware. It would take a long time to train the methods for classes of this size at that time. So it was kind of counterintuitive, but one research group had what seemed to be kind of a crazy idea at the time, which is that actually we need much bigger data sets. And the idea is that, as we know, if you have a small data set, then you can only learn a few parameters without overfitting. And if you can only learn a few parameters, you can never do something very sophisticated. So really, if you want to do something really sophisticated, you need a lot more parameters, which therefore means you need a lot more data so you don't overfit. So that was kind of the motivation behind ImageNet. This data set, which is very famous now, and it was developed in 2009. And the goal of the proposers was really to map out the entire world of objects. So at least the first version of it had 3.2 million images and more than 5,000 classes. So one significant issue is how do you label those images? So images are easy to find on the internet, but images with labels are much more difficult, and especially at that time. So what they did is they used something called Amazon's Mechanical Turk, which is a service that Amazon provides. Let's see. Okay, we're back. It's a service that Amazon provides where you can make a small task for people around the world to do, and they, for example, classifying an image, something that they can click with their mouse, and or maybe type a few words in, and you can pay them like a cent or something every time they do it. So this is what the researchers did. They had, these were academics, they had limited amount of grant money, but they were able to label 3 million images with Amazon's Mechanical Turk this way. And moreover, the classes are hierarchical. So in other words, one of the high-level classes is mammals, and then a subclass of that is placental mammals, and the subclass of placental mammals is carnivore, subclass of carnivores is canine, subclass of canines is dog, subclass of dogs is working dog, and then subclass of working dogs is husky. So you can see there's this big hierarchy. Vehicle, craft, watercraft, sailing vessel, sailboat, trimaran, and so on. So this is how the classes are organized in ImageNet, and this was based on an earlier idea, WordNet, which is a gigantic word database that was done, I think it was in the mid 2000s, that has a similar hierarchical framework where they basically tried to classify all words, make a database of all words. Okay, so once that data set was established, it was used in a challenge, a competition that ran yearly from 2010 to 2017. It was this ImageNet large-scale visual recognition challenge. And every year there's actually several sub-challenges. So for example, in 2012, 3 of the sub-challenges were one of them was classification, where there's 1,000 classes that a given image could be from, and the task, whatever method you propose, has to give the 5 most likely classes per image. And then there's different ways to score it. Maybe if the correct class is one of your 5 most likely, that could be one way to say you got it. Or maybe you could say it has to be the top most likely, and so on. Another competition they had that year was the fine-grained classification, where it was all dog images, and there was 120 categories of dogs, and so you had to design a classifier that could really figure out exactly what kind of dog it was from the image. And another competition was classification with localization, where you didn't hit, it's not only just saying like the image overall is this class, you have to provide bounding boxes. So maybe if this is a mushroom, you would want to provide a box like that or that or that. So you want to classify what's there, but also show where in the image that thing is. Here are some examples of ImageNet images that show how difficult this task is, because images can contain multiple objects. Those objects can be of different sizes, scales, different rotations, different lightings, different occlusions, meaning part of the image part of the object may be not shown. So just as a few examples, like this is mite, but the mite is not centered. Or this is a hard one, motor scooter. Motor scooter is kind of dark. There's also people here. There's cars. There's other stuff. So that's pretty challenging. Or like this one, if you ask me what that was, I would say it's a car, but actually the correct class was grill, and so on. And then this shows for a given classifier the top 5 classes that it came up with, as well as its confidence on those classes. So this particular classifier for this image thought, the most probable class of this image was convertible. Second most probable is grill. Third most probable is pickup, and so on. And here, we have leopard, jaguar, cheetah, and so on. So it's challenging. Like this one is very challenging because I don't know if that should be dog or cherry. The correct label was cherry, but as you can see, this network was almost positive that that's a Dalmatian, and among the other things, it didn't list cherry, so wouldn't get points for that. So that's the challenge, and every year the competitions were a little bit different. But so this is essentially what happened over the years, over the first 6 years, and this is the classification accuracy. I think this is the top 5 error rate. So basically, if the true class is within your top 5, you get credit. If not, you don't. And so, as you can see, in 2010, the different competitors were scoring between 20 and low 70s, and got a little bit better the next year. But in 2012, there's a big breakthrough where a couple methods that were proposed really stood apart from all the rest. And those 2 methods were based on deep learning for the first time. All these other methods were traditional computer vision, so maybe things like support vector machines and so on. And so there was a big improvement in overall performance from the previous year. The top 5 error rate was 15.3%, and that's pretty impressive with 1,000 classes. And the second place winner, as you can see, was more than 10% worse. So there's a big gap. So that was the first year that neural networks came out, 2012. The next year, you can see a lot of people thought, well, I should try this. And yes, performance got a little bit better. And the number of traditional or classical computer vision models shrunk. And then by 2014, nobody was using any traditional stuff. Everybody was using deep networks. And from 2012 to 15, you can see the performance just kept getting better and better. So we're going to take a look at these different networks that were proposed over the years to see how they achieved that. But this thing that's happening here on images or on ImageNet classification is indicative of what's been happening in many fields over the last few years, whether it's engineering or science, all kinds of stuff. People have been moving over to deep networks and finding they can get really amazing performance. Okay, so when we take a look at that very first network from 2012, it's called AlexNet. And the motivation at the time was to build a very deep network. So this network has 5 convolutional layers and 3 fully connected layers. We'll talk more about what we mean by convolutional layer. The fully connected layers are exactly this sort of linear layers that we saw in the last unit. Because this was proposed for a 1,000-way classification, then the final layer is a 1,000-way softmax. And there was various other tricks that were new at the time, but now are very well known. ReLU, max pooling, dropout. We'll talk about all that stuff. And the number of parameters, trainable parameters in this network is 60 million. The number of neurons or nodes in that network, 650,000. So quite large. quite a lot of things to train. That's why you need such a big data set. And at the time, this took a really long time to train this. It was very difficult. Okay, so that's what we're going to be learning more about all that stuff. Let's just first look at some of the components of how these things work. So just to start, let's think about what happens at a single layer of the network, and even like a single, what we call maybe hidden feature of a network. So this is just from the last unit we saw this. So when you have a linear layer, and this is looking at just one scalar output of a linear layer, you have a weight vector transpose the input to that layer plus a bias. So we also saw this back in Unit 5 for classification. And then we take that score, or logit, and we put it through this activation function. Maybe it's a sigmoid, and we get our activation. So as we saw last time, we can interpret what's going on based on our knowledge of linear classification. So if we just have this single layer in isolation, basically we know that, and this is just, imagine that we have two features just so that we can draw things. We know that there's essentially a decision boundary associated with this, what basically is a linear classifier. That decision boundary is perpendicular to the weight vector W here. And what B does is B shifts that thing so that affects the intercepts. So that's the role of W and B. And you can think about this as effectively splitting your feature space into two half spaces. In this case, the blue and the yellow. Because it's a linear classifier, the half spaces are linearly separated. And this is basically a building block of what this deep network is doing. This is one little building block. Something to keep in mind, sometimes we could say that the output A is tuned to W in the sense that if you think what is the input X that makes A the largest? Well, the way that this activation function works, this activation function tends to be increasing. So if you want to make A large, you should be making Z large. And then over here, if you want to make Z large, we can use Cauchy-Schwarz to bound this term, W transpose X. So this is less than or equal to the norm of W times the norm of X. So that's the largest this could be, is that product. Moreover, you get the equality, meaning you get that largest value when X is some scalar C times W for a positive C. Okay, so basically if you want to make A large, you want to make Z large, you want to have X pointing in the direction of W. Okay? And that makes sense. You can, as we've talked about before, the samples which are furthest from the boundary on this blue side would give you the largest scores. The ones that are furthest this way would give you the most negative scores. So in the sense of scores being large, in this case, you'd want to be, let's say, on the blue side. Okay, so that's how you can understand a little bit about one piece of this network, what it's doing. Okay, now when we have two layers, we can put those first pieces together to do something more interesting. And this is what we saw in the demo of the last unit. So in the last unit, this is very similar. We have these are the heat maps of the hidden activations. And as you can see, these heat maps are individually, they look like the pictures over here. But each hidden node has a different boundary. And so if you have a boundary here, and a boundary here, and a boundary here, each one of those we can think of as generated by a linear classifier. That's what the first layer does. And then the second layer takes those boundaries and looks at the intersections of those half spaces. So for this particular case, if you want to be, a blue sample is basically going to be something that's to the right of this line, something that's to the southwest of this line, and something that is to, let's say, the northwest of this line. And if you intersect those three half spaces, that's how you make this shape here. Okay, so these little building blocks, they can, even though it seems really simple, with another stage, you can make them do more interesting things.
So, just with the inputs, I noticed that,
Yeah, so to make sense of this, this would be the heat map corresponding to the input. So in 2 dimensions, x1 is just going in this direction. So, the further you get to the right, the larger x1 becomes, the more blue it gets. And x1 is invariant to the vertical direction. That's why there's no change in the heat map vertically. Same thing with x2, but in the other direction. Yeah, so this is called TensorBoard, this visualization tool. It's called TensorBoard X in PyTorch. You can play with it if you want. It can show you what's going on inside your network. You can kind of take a peek. Of course, it works best for small networks because once things get really big, it's just really complicated to understand what's going on. But we can still get a little bit more complicated. So what if we have this data set? So the blue points are here, the yellow points, you can see them. This is called the Swiss roll. So can we use that same idea to classify this? And the answer is yes. Maybe we need another layer. Maybe we need, in this case, 3 layers, or actually 4 layers to do this. But it's the same idea. You have these first heat maps. They all look like linear boundaries, right? And then just half spaces. Then you intersect those half spaces, and you make things like this. This is kind of like a little splotch like this. You can see this one is something like that. This one is like that, and so on. And then you can intersect all those shapes, and you can get more interesting shapes like that. And then you can intersect all of those, and you can finally get these classification boundaries, which you can see do a pretty good job of classifying those blue samples. So with increased depth and increased width, you can start to do more and more interesting things. So basically, it's all about hierarchies of these transformed patterns. Any questions about this so far? Okay. So those are just sort of, toy examples. So what about something that's like a real classification problem, like cats versus dogs? How do we do that? So for that, we need a few more tools. But still, overall, the idea is very similar. You have to build what we call features. Features are just the intermediate stages of data in the network. You build features that at the left side of your network, towards the input, are pretty simple. So maybe they look like things like that. And then you combine those features to give you more interesting shapes. You combine those features to give you yet more interesting shapes that you can see start to look like eyes and ears and noses and so on. And with those building blocks, you can combine them to get even more interesting shapes. So the idea is still to use hierarchies, more layers, but also more sophisticated 2-dimensional processing. So we're showing little images here. That's because we're doing processing in 2 dimensions, and that's the next thing that we need to talk about to understand what's really happening in these deep image-based networks. It's convolution is essentially we have to learn about. Any questions so far? Okay. So what's very interesting is that biologists who study the brain have found out that the brain actually works for when the visual cortex works in a very similar way as these neural networks. So they think about the brain as having these different regions. So V1 is the part of the brain that's connected most directly to your eyes, and then V2 is behind that, and so on. And as you go from V1 to V2 to V4 and so on, the representations get more and more sophisticated. And so they've done some interesting experiments, let's say with V1, where what they do is they'll focus on maybe a particular neuron. We'll measure what's happening at that neuron after showing the person or the animal different patterns, different visual patterns. And what's really interesting, what they find is that there are different neurons that are tuned to exactly these fundamental shapes, these little building blocks. And then those early neurons, they're connected together to get the neurons in the next layer and so on. So the brain is also working in a hierarchical way, very similar to a convolutional neural network. Okay, so just a little bit about history. The very first deep network from 1965. First convolutional deep network, 1980. First time people were working on backpropagation in neural networks or deep networks was in the 80s. In those days, as we know, when you have limited training data, if you try to use a lot of parameters, you get overfitting. So that was one issue. They had limited computational power, especially relative to today. And there's another problem, which is an architectural problem called the vanishing gradient problem. And that's important to understand. So let me draw a little picture here. So if we think about the sigmoid activation function, maybe it looks something like this. And if you think about the sigmoid, as we know, you have to compute slopes. When you do backpropagation, you take a gradient of every layer, and then that gradient gets passed through backpropagation and becomes part of the gradient for the next layer down the chain, right? So when you look at the gradient of this shape, or the slope of this shape, I'm sorry I didn't draw this very well. This red should be going through the origin, but right at the origin, the slope of this is 1. That's the largest slope you get for this sigmoid. Or I guess I drew the tan H. The sigmoid would be shifted so that the 0 is down here and 1 is up here. As you get away from the origin, the slope decreases. And as you get just a little bit outside, the slope is almost 0. And so that's a problem. So if you have a feature in your network that's out here, when you do backpropagation, you compute that slope. That slope is a very small number, and you pass that back a layer. The same thing can happen again and again in a deep network because it's going to go through a lot of sigmoids. So every time you go through this, it gets smaller and smaller and smaller. And by the time you get to the front of your network, the gradients have essentially vanished. They're tiny. They're unusable. So when you train, the things towards the end of the network get trained, but the things at the beginning never really get trained. So this is called the vanishing gradient problem. And it was a problem that in the very early days, people probably didn't realize this or they didn't understand it well. So one of the things that was done to alleviate this was this ReLU activation, which we saw. ReLU it's like that. So the gradient or the slope here is 1, right? It's always 1 wherever you are. So if you have a positive sample and when you do backpropagation, the gradient does not shrink at all. Of course, here it's 0. So, but you probably wouldn't have. We need this nonlinearity for the network to work. We said if you take out the nonlinearities, then you just have linear cascades of linear stages, which is just like another linear stage. And we know that something like linear regression, linear classification doesn't really do very much for us. So we need these nonlinearities, but this ReLU, in terms of the vanishing gradient, is a really good compromise between something that's nonlinear and something that preserves gradients in backpropagation. So this was one of the tricks that really helped things, and this is still probably the most popular activation function that people use today. There are activations that are better, but in many cases this works well enough that that's what people use. Other things that are important are convolutional layers, which we'll talk about in the next few slides, and pooling layers, and all sorts of other tricks that we'll talk about: batch norm, dropout, skip connections, and so on. So just to start our journey with convolutional layers, essentially, as I mentioned before, when you look at what's happening in the early layers of a neural network, you're trying to find these little building block patterns. And the little building blocks might look like things like this. So in these pictures, gray would be 0, white would be positive, and black would be negative. And so, for example, like this thing is, there's a little bump here, a little dip behind it, and that's like a little fundamental building block shape that is, angled in a certain way. And then you have other ones that are angled in different ways and so on. You also have these, almost looks like a Gaussian type of bump, and so on. Here's a dip. And with these little building blocks, you can put them together to make more interesting things, which can be building blocks for yet even more interesting things. So that's the sort of hierarchical stuff we want to do. And so when we think about what's happening in an early layer, it's essentially building some way of detecting these little building blocks within an image, these little things within an image. And one thing that's important is we expect that these little building blocks could be located anywhere in the image. So we don't think that they're necessarily going to be located one place or another place. So we can think of these patterns as translation invariant. We want some sort of linear stage that's not just a matrix multiply. It somehow is going to look for the location of and existence of these patterns throughout our image. And so we can think about that as sort of a pattern matching problem. So basically it's like, how do we find one of these little local patterns? Well, imagine that we have a template, we shift it around, and we take an inner product each shift, and we look for where we get a big inner product. So visually, imagine that our template is this little 4, and imagine that our image has all these different digits in it, and we want to look for the 4s, the location of 4s in our image. So what we do is we take this template, and we just slide it around. We slide it all the way around our image. And for example, if that template was located over here, we would expect to get a relatively big output because this thing looks quite a bit like our template. On the other hand, if the template was, in other locations, we get something, but it wouldn't be as big. So just by moving this template around, and once it's at a certain location, we want to do a pointwise multiply between the elements in the template and the image below, and sum them all up. And if you remember, that is what the inner product between matrices is. Inner product between matrices, it does what pointwise multiply of the matrices, and then just sums all the values. Question?
Isn't this operation quite costly? Like, you were to run it on a big image, and our template is also.
Well, it depends how big the template is. So if the template is like 3 by 3, then it's going to be like 9 multiplies for every shift. So whether that's costly or not, in terms of today's computing hardware, you can do that really quickly. But yeah, all this stuff is kind of costly, but we're relying on the fact that, today in 2020, we have really good computing hardware that can do all this stuff very efficiently. But it's definitely an important piece of being able to do all this, is to have that hardware. But you're right, as the template gets bigger, it becomes more costly. Right, just the cost per pattern match grows with the number of pixels in that template. So, okay, so let's write this as an equation, because this equation is important because we're gonna see more complicated versions of it, so we at least need to understand this one. So we're gonna call the template this. So this is our template. And so this is a little matrix, and we're going to use K, in this case, to index over the, let's see, it's going to be the vertical and horizontal coordinates of that matrix. So K1, K2. And then we have our underlying image, X, and we also have the location of the template within this image. So the J's are going to tell us where we have slid the template to. So here would be zeros, and as we, this would be increasing J1, this would be increasing J2, and for a particular J1, J2, the template's there. And this is how we would do this pattern match. As you can see, this is sort of the anchor within the image, and then this is the deviation from that anchor, K1, deviation vertically, K2 horizontally. And for every one of these little offsets, we do this multiplication, and finally we sum up all the values, and we get one scalar number at that location. And so this is finally the output location, J1, J2. So is this equation making sense, how the different indices are coming into play? So you have basically this is the location that we're sliding the template to, and then these are these intermediate variables, temporary variables that are being used to move the pixels around in our template and the offsets from J1 and J2. So this is essentially what we want to do. And just to connect it to maybe other classes you've taught, in signal processing, we refer to this operation as correlation. And look, this is exactly the equation from the previous page. But if you take a signal processing class like 5200 or 3050 or other ones, convolution is a similar operation, but where you have minus signs here. So it's kind of like you're doing this, but you're just flipping the template around vertically and horizontally before you do that pattern match. Okay, so that's the difference between correlation and convolution. Small difference. Sometimes this first one is called convolution without flipping and reversal, whereas this one is called convolution with flipping and reversal. As you can see from this page, we don't really need the flipping and reversal to do machine learning. It's just sort of an extra step that complicates things. So essentially, we don't do it. So when we do neural networks in PyTorch or TensorFlow, and when they refer to convolution, it's actually correlation. It's convolution without the flipping and reversal. That's good enough to get the job done. And so convolutional layers or neural nets really are just doing correlation. And we always call these weights, this W matrix, the kernel. That's the little template that we're moving around. Okay, so it's a good place to stop for today. We'll get into some more details next time. See you guys on Friday.